Hello, my name is Lucía Absalom Bautista, and this summer I've been working on Project 2218 at the Faculty of Mechanical Engineering of the University of Ljubljana. My mentor, Jan and both and me have been trying our best to make our code run by debugging the code from small errors and implementing MPI on R. So, let's start by explaining a bit what our goal was. We basically have data about different consumers, and we want to compute some models that will allow us to predict their electricity consumption. In times like this, a good daily electricity consumption forecast for a population is crucial information, and that's why I personally find this topic particularly interesting. We are computing the following models widely used in prediction, and we are implementing our code on R. The dataset, which consists of, as we said, electricity consumption data retrieved for individual houses, companies, factories, etc. And along with this data, we have some information about the date the data was retrieved, if it was a weekday or weekend, for example, or the weather, all used for the later computation of the model. For each IDs, this is how we identify each consumption unit. We retrieve data every 15 minutes, and all this data is stored on a MongoDB's database. This database is stored on a cluster, and we call some functions that oversee collecting the selected data. For this, we use an API and some GET petitions, and we receive our data as a JSON object. On var consumer MongoDB, we also store the vector of all the IDs that we're going to use to compute the models. So when I start playing with the code, parallelization was already running, after doing some small debugging concerning RNA's treatment and lack of data. So the problem was that our computational limit reached 100 IDs, which already took something like 3 hours to run. So our goal was to extend this list of IDs and go up to at least 1,000 consumers. For this, we decided to use MPI. We will describe the parallelization process, which has been done using the library doParallel. Inside the library, we find a collection of functions that inside the node make the parallelization of the code. So for our computations, we define a function fz, which will collect our data and on the selected dates and compute the models, in this case random forest. These models are stored as functions on different files that we import at the beginning of the code. After computing the model, we save it as an R data file for its later use. After defining the functions, we just need to detect the number of cores and apply one of our parallelization functions, passing the arguments cores, data and model. We check the time it takes to compute, and that's it. So let's go now to MPI. We are using a library on R called RMPI. Our code basically consists of two different files, a master file that spawns the slaves processes and the slaves that do the computation. The master file distributes the tasks along the slaves, so each one computes a model for a subset of the IDs that we chose in the beginning. Here we can see how the code works and how, depending on the rank of the slave, it's going to compute some IDs or other. The parameter that we are going to be playing with here is n, which is going to choose the amount of IDs we fetch. So let's go now to the slave file. Each slave of rank k will compute n elements in total. So this is an example of how our code looks like. Now we have our code finished, we just need to send it to compute. For this, we will use a batch file, and Absalom will be in charge of allocating the computing on display nodes. Here's an example of how our batch file looks like it. We just need to do sbatch and we have finished. So now we only have to show the results achieved. Before anything, I would like to say that we had some problems with our cluster, where the database is located, so these past days it hasn't been running so well. The results here shown are only for 2 nodes, but we have made the code running up to 8 nodes. So for n equals 20, you can see scaling goes very good for normal for loop, mac-apply, parallel-apply, parse-apply. These are results. For n equals 40, more or less the same results. And for n equals 80, we still have good scaling and good results. So this is all my project, but I also been working on another project where we are basically working with an exact solver of the minimum sum of square clustering, and we want to compare for different datasets, real and artificial. If when the number of clusters equals the ground truth, we get different quality measures. The plot twist here is that no, and our goal has been to find reasons why not. My main contributions to the paper have been plotting the different measures for different datasets and reviewing some literature on the topic. Thank you very much.